Okay, so let's continue talking about our SN1 and SN2 reactions now that we discussed just general ideas of the electrophile and the nucleophile and the trends that you see in those. A reminder that the SN1 reaction is unimolecular, and so in the kinetics, this is how it reacts. We're going to be focused on the concentration of the electrophile. So here we're looking at a substitution of a tertiary alcohol. Remember, in SN1, the tertiaries react faster than secondary, which reacts faster than primary as far as the starting molecule we're looking at, in this case, an alcohol. In our reaction that is being studied here, this is starting with an alkyl halide, not an alcohol, and making an alcohol. But similarly, tertiary alkyl halides react faster than secondary alkyl halides, which react faster than primary alkyl halides. And what you'll notice is that the electrophile, this is the area that is going to be gaining electrons in our reaction, is what determines how fast the reaction will go. So if we were to write our rate law, it would just be dependent on the concentration of the starting electrophile. Here, that is our alkyl halide. So our nucleophile is water, and if you remember from our last trend, water is a not very strong nucleophile, it's kind of weak. But again, the rate of this reaction is just going to be dependent on how much of that starting electrophile we have. And that's because only the electrophile is involved in the rate determining transition state, right? Remember, for these SN1 reactions, that slow step is that we first have to remove the leaving group. In this case, it's bromine. And we make our carbocation. Once it's removed, then we can add on our new group, our substituting group, and make our new product. So because the main rate determining transition step involves that compound that is the electrophile, for example, here in the transition state, the leaving group is separated from the electrophilic carbon, and it takes its electrons with it, right? That means that this molecule, which is from our electrophile, is the only molecule that's involved in the rate determining transition state, the slow step, and thus it is the only thing controlling the rate of the reaction. So for an SN1 reaction, the electrophile is the only molecule that controls the rate. Oh, sorry for this blocking here, but this is just a reminder of that reaction diagram. Again, you can see that for an SN1 reaction, remember that the first part is you're going to have this loss of the leaving group, the slow step for our alkyl halide, and then you have attack of your weak nucleophile, that's our water here. And then in this case, when we're forming an alcohol, loss of a proton. Now, if you go back to chapter 5, what you'll see is that these exact steps are somewhat different. And that's when we were looking at taking an alcohol and making an alkyl halide. Here we're looking at taking an alkyl halide and making an alcohol. Now, the only step that is different as far as arrangement is this step. In our chapter 5, we started with addition of a proton and then went through the same steps: loss of leaving group, attack of nucleophile. Here, where we're starting with our alkyl halide and making an alcohol, we start with loss of leaving group, attack of weak nucleophile, and then this step, the loss of proton. So the protonation step is the only step that is rearranged. Again, the key step in these reactions is this, loss of the leaving group. This is the slow step. Now, because the nucleophile in an SN1 is typically a weak nucleophile, this is key. If you see a weak nucleophile being used, it's typically an SN1 reaction. It's usually a liquid, and generally that same nucleophile can be used as the solvent in the reaction. So when we're talking about this physically, you're actually hands-on reacting these chemicals. The solution, the liquid that you are putting these items into is also usually the nucleophile. In particular, this tends to be things like water, ethanol, or methanol. These are all liquid solvents. Again, water being the main one that you're probably most familiar with. These are all liquid solvents, and they are all also weak nucleophiles. So if you see a weak nucleophile, it is usually an SN1 reaction that's occurring, and that is usually the solvent that everything is dissolved in. And the reason you want to use the nucleophile as the solvent as well is because it ensures that as soon as that first step occurs, right, so the loss of the leaving group, the carbocation that is now made is captured by our nucleophile, right? Because the nucleophile is the solvent, it's everywhere. So as soon as we lost our leaving group, we want to, for example, in this case, add water on. So if water is what is everywhere, if it's what the reaction is dissolved in, then you have a better chance of quickly adding that nucleophilic molecule on. These conditions where you're using the nucleophile as the solvent itself also can be used in SN2 with weak nucleophiles, though you, again, are going to typically see this in the case of an SN1 reaction. Now, a reminder of the arrangement of SN1 and SN2. We talked about this before, but remember that the carbocation intermediate of an SN1 is achiral. It's not chiral. That's as long as there are no other chirality centers, for example, on the rest of the molecule. If it was a long molecule and you had multiple chirality centers, then of course the other chirality centers would still make the molecule chiral. But as soon as you remove a leaving group from your reactant and you form a carbocation, the carbocation does not have any chirality. It just has 3 groups on it, a positive charge. There's no chirality. And our second step in an SN1 is that you then add the nucleophilic group on. So in theory, the nucleophile can attack from either side with equal probability, and generally you would make a 50-50 mixture of some type of chirality So if you start with a chiral molecule, you get rid of a leaving group, you form a carbocation, and our new group can come in from either side. Again, in theory, 50-50 mixture of an R or an S chirality. Now, this isn't the real truth of it. Generally, you see unequal mixtures where you do still have a mixture of R and S, but generally the mixture is not completely 50-50. And again, we talked about this before, that's probably because that the leaving group doesn't just fully detach quickly and move away from the carbocation. It can tend to hover near that carbocation and kind of block the way for the entrance of the nucleophile. So what happens is that most of the nucleophilic attacks occur on the side away from where our leaving group is detaching, although some of the attacks can occur on the side where your leaving group was previously attached. So for example, if you start with an R configuration, more of your product will be S. It'll be from the opposite side, right? If this side was R and that's where our leaving group was, it's going to enter on the S side. But some will still be R, so there's still potential that it can enter on the R side. So you get what's called partial inversion. Not a 50-50 mix, but partially inverted to the opposite chirality, though with some mixture. So again, here is a example of that. You have a carbocation leaving group and ion pair. Here's the carbocation that is formed once our leaving group leaves. And during this step, if some of our nucleophile attacks, it can occur in a way that is faster from the back. So you have more inversion of the configuration than you do retention of the configuration. That's what we just talked about. So you'll have more than 50% that is inverted and less than 50% that is the same. Now, once this completely moves away and you have your carbocation that is completely bare, again, you can have a nucleophile attack from either side. And at this point during the reaction, you get a 50-50 mixture. Remember, we also talked about carbocation rearrangement, which can occur in SN1. And we want to look for this when you have secondary alkyl halides or secondary reactants. So your starting reactant, if it is a secondary reactant, the final product could, for example, yield a tertiary product if it is one carbon away, one carbon rearrangement, or if you have a hydrogen rearrangement. Generally, what you're going to be looking for is if during the formation of the carbocation, you can form a more stable tertiary carbocation, then you're likely to have a rearrangement. If that rearrangement is only one away, one bond away, you'll form that tertiary carbocation, and then your product will thus be a tertiary product. So again, only adjacent groups can migrate.